In this lesson, we consider how we generate nucleophilic carbon species. So, with the exception of CN- cyanide, molecules with a negative charge on carbon are not very stable, and they need to be generated from a neutral molecule as a precursor. So the remaining 3 carbon nucleophiles that we've talked about, the alkyne anion, the enolate, and the double enolate, can be generated by deprotonation of the conjugate acid using a sufficiently strong base. So one example in the generation of an alkyne anion, alkynes have a pKa of 25. So a base like sodium amide, NaNH2, is sufficiently strong to quantitatively generate the alkyne anion because sodium amide is the conjugate base of ammonia, which has a pKa of 38. This reaction is favorable by 13 pKa units. Enolates are frequently generated. They can be generated from sodium amide also. They are actually frequently generated using lithium diisopropyl amide, which is also abbreviated and referred to as LDA. So the pKa of an alpha hydrogen to acetone is 19, and LDA is the conjugate base of diisopropyl amine, which as an acid has a pKa of 33. So this is also going to be a favorable acid-base reaction by 14 pKa units, so it will go to completion. The advantage of the double enolate is that it is a much weaker base than the single simple enolate is, and it can actually be generated quantitatively using sodium hydroxide as a base. Okay, so the hydrogens alpha to 2 carbonyls, because of the additional resonance stabilization, have a pKa of around 10. And water, of course, has a pKa of 16, the conjugate acid of NaOH. So NaOH is a strong enough base to generate this, as I said, quantitatively. So in the rest of this lesson, we're going to focus on enolates. And as you can recall, enolates have 2 resonance structures. There's the immediate structure that you get from removing the hydrogen that's bound to carbon, which of course puts the negative charge on carbon. But what stabilizes it is the second resonance structure, in which the negative charge is on the oxygen and you have a carbon-carbon double bond. So given that the enolate has these 2 resonance structures, if you were going to protonate it, theoretically it could be protonated on either the carbon, which would take you back to the ketone, or it can be protonated on the oxygen to produce what's called an enol. And enol has that name because you've got an alcohol directly bound to an alkene. So one of the carbons that is participating in the carbon-carbon double bond has an alcohol bound to it. Now, ketones and enols are structural isomers. They are not resonance structures. Yes, you've moved electrons, but more importantly, in going from one structure to the other, you have moved a hydrogen atom. And once you move atoms, they are not resonance structures. However, even though they're structural isomers, they are readily interconverted under either basic conditions, as we have just seen, or under acidic conditions, as we will see in a few minutes. So they are actually, the 2 forms are in equilibrium with each other. I want to introduce one more term to you at this point. Structural isomers that are readily interconverted are called tautomers. So the enol form and the keto form are 2 different tautomers. So if we're considering an equilibrium, we need to consider which of the two forms is going to be favored at equilibrium. And in general, the keto form is favored. The enol form normally will exist only in very small amounts. Okay, so in the examples given for acetone, it's not greater than 99% in the keto form as opposed to in the enol form. Cyclohexanone, the enol form, is slightly more prevalent. It's 1.2%. But as you can see, in most of these cases, there's just a small amount of the enol form. So little that it is rarely even detectable in solution. So why is this the case? Well, the argument is going to be a thermodynamic argument. The keto form is more thermodynamically stable. And when we're talking about thermodynamic stability, the numbers we need to consider are bond strengths. So for the keto form, we have a CO double bond. And when we want to get the strength of a CO double bond, we need to add up the strength of a CO sigma bond and a CO pi bond. You add those two together and you get 176 kilocalories per mole. There is also a CH sigma bond that is present in the keto form, the bond between the alpha carbon and the alpha hydrogen, that is not present in the enol form. And a CH sigma bond gives us a bond strength of 99 kilocalories per mole. If you add these two together, you will get 275 kilocalories per mole worth of bond strength. Now we're going to contrast to the enol form, and we're only looking at the differences between the keto form and the enol form. So in the enol form, instead of having a carbon-oxygen double bond, we have a carbon-carbon double bond. So again, when we add the sigma and the pi together, we get a bond strength here of 146 kilocalories per mole, not quite so much. And then instead of having a CH bond, we now have an OH bond. That helps us a little bit. That's a slightly stronger bond, 111 kilocalories per mole instead of 99. But when you add those together, you end up with 257. So you have stronger bonds in the keto form than you do in the enol form, and therefore the system overall is energetically favorable. The exceptions, and we do have to consider these, is that the enol form will be favored at equilibrium if that form permits conjugation or even better aromaticity. So for example, if you look at 2,4-pentane dione here, the di-keto form will only exist 24% at equilibrium. 76% of what's present is actually going to be the enol form. For two reasons. First of all, the enol form is conjugated. The CC double bond and the CO double bond are conjugated with each other, whereas in the di-keto form, those two double bonds are not conjugated. They are separated by two single bonds and not one single bond. And secondly, there's actually the opportunity for an extra intramolecular hydrogen bond between the OH hydrogen and the carbonyl. That would give a nice six-membered ring. So that's additional stability to the enol form in this case. Then aromaticity is most expressed if we look at phenol. Okay, so the enol form is much more stable than its corresponding keto form. So we mentioned before that you can convert a keto form to an enol form under basic conditions. You simply deprotonate it and reprotonate it. So deprotonate on carbon, reprotonate on oxygen. But I mentioned that these compounds are in equilibrium under either acidic or basic conditions. So we have to finish this lesson by considering the acidic mechanism for enolization. So the acidic mechanism begins like every other acidic mechanism involving a carbonyl group. You begin by protonating the carbonyl oxygen. However, in the second step, instead of a nucleophile coming in and attacking the carbonyl carbon, a hydrogen is removed from the alpha carbon, which is now quite acidic because there's a positive charge on the molecule overall. That hydrogen is even more acidic. It does not take a particularly strong base to remove this hydrogen. The electrons from the CH bond form a CC double bond, and then that subsequently, as you follow the arrows, breaks the CO pi bond, putting the electrons onto the oxygen to restore neutrality. Okay, so this acid mechanism is a protonation step followed by a deprotonation step, in contrast to the basic mechanism in which you had a deprotonation step followed by a protonation step.